right? We're missing a lot of students, but anyhow, hello and welcome. So as per request, as usual, so hello and welcome to another lecture for 2DM3. As requested, I put some background music. If it gets loud or annoying, please let me know, and I can either reduce it or turn it off. All right. So okay. So someone said to keep it on, so that's great. So maybe let's talk a little bit about the midterm and things, and then we'll begin the lecture. So let me show you some. Let me share my screen with you. Screen 2. Okay. And let me just open this up. So everyone should be seeing my screen right now. If not, please let me know. Keep this right here in case you message me. Okay, so let's turn this off. Okay. So I just want to talk about some things for lecture today before we get started. So there is an announcement. So a lot of people are asking some questions. If you go to Avenue, we put up a announcement after the midterm to clarify some doubts that some of you might have had. So just right here about stuff we're going to do for the future. So in case some of you are concerned, some stuff that we're going to do right now for some of you who are worried about submitting it later, and just some general stuff that we're trying out. Okay, so definitely please read that, and if you have any questions, let me know. Somebody asked about Tammy. Go to the lecture, the abridged lecture notes. There's an icon right here, and it will cover a lot of colors. You were asking about the difference between gold or light gold or khaki, and you can have whatever colors you like. So that's set up there.
Wow, I'm so glad. I'm so glad I asked about it now.
Yeah, so the colors are there. Yeah, so it will teach you the colors, and you can click on them and try them out as you like. So here's cayenne, and here's thistle 1 and thistle 2, and the whole page changes accordingly. So a nice, a nifty way to learn about colors, I guess. So that's there. Another thing I just wanted to show you is an image I found on Twitter. So give me a moment. Where is it? This one. So just get that ready and prep for today's lecture. All right, so unless there's any other questions, let's begin today's lecture. So anything else? Any concerns, queries? All right, then. Let's do that. And here is the first. Okay. So why don't you guys look at the slide, and maybe someone can tell me what's wrong. The blue items are these are theorems without names. They're in the book. They don't have a name. So just pointing that out. But can anybody find the problem? Otherwise, we have true equals false. So can anybody find the problem? Oh. Boop. Boop.
Is it that you distributed the negative over both P and Q?
Yeah, exactly. This is the problem right here. Is that Tammy?
It's Alexandria.
Well, talk to me more, Alexandria. I will learn. But yes, Alexandria is exactly right. This is the problem. This is a poor choice of names. So the book calls this a 3.9 distributivity, but we won't call it that. We'll call it mutual commutativity of negation with equivalence. So the rule is not P equivales Q is the same thing as not P equals to Q. Okay, so that's the formal rule. Hopefully we'll learn how to put more Unicode in here. but that's the rule, and so that's what 3.9 says. But the name is misleading, so I just wanted to point that out. Okay, dokes. Let's get rid of this. So we're gonna pick up where we left off last time. So we just wanted to have some real content matter for chapter 3, and sorry, we wanted to have some real content matter for the first midterm, and that's why we covered chapter 3.1, negation, false, true, and equivalence. So I'll go over that really quickly. But today we want to talk about chapter 2. Okay, so please read chapter 2, and we'll wrap up chapter 2 today, and we'll jump into chapter 3 tomorrow. Okie dokes. So that's the plan. All right. So as mentioned before, a propositional variable is just a variable that is either true or false, and a lot of expressions. So let me just point at some of these. So a lot of expressions, such as equality, return either comparisons, return true or false. This is just a comparison. Is the left-hand side equal to the right-hand side? Is this string hello a subset of hello world? When I look at the commonality between two sets, is the commonality 2 and 3? All right. So these are just examples of propositional statements. Okay. So just a quick review to remind some of you. There's a really interesting property. So I mentioned last time that when you were little, you learned about multiplication tables and addition tables, and now you're learning about truth tables, which are essentially the same thing. The cool thing about the Booleans, the propositions, is there aren't that many operations you can do on them. So for the natural numbers, you can add, you can multiply, you can do integer division, you can do a lot of things on the numbers. You can exponentiate, you can do a lot of operations on them. But for the Booleans, this might be a bit surprising. So let me just write this down for you. This is, I think, a non-trivial thing, and I think it's pretty neat. There are only 16 operations on the Booleans. So that's 16, there are only 16 binary operations on the Booleans. So given two Booleans, what can I do with them? There are only 16. And that's because the Booleans are a finite set. So we'll talk about this in a moment. So let's look at unary operations. What are the unary operations that can happen, right? So there are only 4 unary ones, because a unary takes either a false or a true, and it returns either a false or a true. All right. So these operations, given a false, I can always return false, right? And if you give me a true, I just return false. So this column is the always return false operation. Okay. The one over here is the always return true operation. If you give me false, I give you true. If you give me true, I give you true. This column is the identity. It's do nothing. If you give me false, you get false. If you give me true, you get true. And this is the only interesting one, which flips the two values. It's negation. Okay. So this is all of the unary functions on the Booleans. Only 4 of them. And the reason that there's only 4 is because you have two possibilities for the input and 2 possibilities for the output. And so 2 to the power of 2 is 4. So there's only 4. If you don't follow the counting class. But it's just interesting that there's only 4 unary operations, and the identity is nice, but negation is kind of the only useful one. So that's pretty neat. Operators, just negation flips them. If we name the operators, like F1 is the everywhere false, no matter what the green input is, the output is always false. Okay. The identity, all right, no matter what the input is, it just leaves that input alone. It does nothing. It's do nothing. All right. And finally, the everywhere true operation takes the input and returns true. Is there a question? Okay. So I just want to show you that negation is kind of special here. It's kind of the only really interesting one. All right. So how many binary operators are there? So as I mentioned earlier, well, for every output, true or false. So for every output, there's 2 of them. We need to consider a way to get that using any of the input-output pair combinations. So that's going to be 2 to the power of 4. So there's 16 binary operations, which is really neat. Again, don't worry if you're not comfortable with accounting. We'll get to that later on in the class. Just wanted to mention it now in case you're interested. Right, how to count the number of total functions on between binary sets is something that we'll get to later on. So let's look at conjunction, for example. Right. So conjunction, right, can be defined by looking at the second element. If it's false, the whole thing is false. Likewise, we can do similar things for inequivalence, and a few of the operations we can, but not all of them. All right. Is there a question? Okay. So the cool thing is, when we look at the operators, we find that here's the everywhere false again. No matter what the input pair is, if you give me false and true, you get false. If you give me true and true, you get false. If you give me false and false, you get false. True operation. And returns true when both items are true. Okay. We have or. We have equality, which only returns true when both of the items are the same, right? And then we have implication and reverse implication. And these are like orderings, like less than or equal to on the numbers. So let me just point that out. Some people are not as comfortable with implication. We'll get to implication tomorrow. Just want to write that out. So P implies Q is kind of, all right. So we'll get to that tomorrow, and a bunch of stuff I say in lecture, you might want. I do want to let you know, they're not really abridged. They kind of contain extra material. They're really the supplemental lecture notes. They contain what's on the slides and then extra information, like this relationship about implication and less than or equal to. That relationship is really, really, really close. Implication is an order. And in some sense, the ordering is an implication. So it's, you can find more. These. A bit of trouble reading them, so I'll just talk about that a bit quickly. So this is just equality, right? Just as you've always read it, equals from. This is differs from or inequality, the second one. The V is or. You think of a V as like holding water, right? And I don't know why that's the analogy used. The upside down V is and it's almost like an A, if that helps. The arrow is an implication, if then else, and it's kind of like if I have B, then that leads to C. The arrow is like that. So B is as B. Okay. And again, these things are on the lecture notes in case you want to learn more about them. And of course, in the book, chapter 2. So we keep bringing up this table of precedences to remind you when you don't and when you do need parentheses. So in particular, equality and inequality, whenever you have a conjunction, for example, if you have a this and that, and they contain equalities, the equalities don't need parentheses. They have higher precedence, right? Then you have and or, and then you have the implications, and then finally the equivalences. Okay, so whenever you have a chain with an equivalence, that means everything else gets parentheses, but not the equivalence. The equivalence is the lowest precedence thing, right? So this is the main distinction. Equality is up here, equivalence is down there. Okay, and don't try to memorize the table. You just you do enough practice and you'll internalize it. Okay, ducks. All right. So here's just some ways you can read these. In particular, we've covered how to read the other ones, but the way to read not is interesting. Sometimes away. English thing. have one equal sounds a bit weird. Not the case that, which sounds possible. Okay. All right. So here's an example of how AND works. All right, just to show how a few examples of these things. 1 + 1 is 2, and the sun is a star. So the word "but" in English is usually translated as an "and," and in all other cases, it's false. And it requires both pieces to be true. All right. Implication is just it requires the first one to be second one to be, or to be the first one to be true. Right. So notice it's false right here. The moon is green if 1 + 1 = 2. So the part after the if is true. The part before the if is false. That's the only time it's false. Another way to think of if or implication is that it's ordering the Booleans. True is up here and false is down there. And then you have an implies this way, right? So false implies true. False, true, implies goes that way. So whenever you have two things, you just put them like that and go up. So in particular, false implies anything, because if you have a false implies anything up there. Okay, so that's the first example, for example. So we're reading it this way. So here, false implies true, right? I have true things if I have false stuff to begin with. Assuming nonsense, okay. So let's move on. Right. Cover this next example here. So to stay dry, it's necessary to wear a raincoat. Right? That is to say, if I want to do this thing, then this other thing must happen. That's usually what the word necessary means. And that's formalized as an implication. Right? So these are phrases you've probably seen in mathematics, like calculus. The other one is to stay dry, it's sufficient to wear a raincoat. That is to say, to stay dry, I can stay dry provided, right? Or if I wear a coat. And this is reverse implication. Okay, so really, so these are perhaps the most common ways you will see implication in informal mathematics. So we won't do a lot of formalization in this class, but we'll do enough to get you practice with it. All right. So when you say even if, what does that mean? All right. So this is another one that some people like to ask. So for example, 1 + 1 = 2, even if the sun is a star. Okay. Well, 1 + 1 = 2, regardless of that fact. What about here? The moon is green, even if 2 + 2 = 7. Well, both of these are false. And even if the second one was true, it doesn't help in the first case. So the way to formalize these is to say the first one is true, all right here. The first one is true, and even if the second one is true, I still get the first one. Okay. So let's say that again. The first one is true, and even if I have the second one, the first one remains true. All right. And hopefully after Friday, you'll realize that this expression is provably equivalent to just T. All right. So you can simplify it even further. So this even if part means you can throw away the rest. All right. So this even if that means just this. Right. So that's a nice, cute little thing. Right. And it's summarized right here for you. So 1 + 1 = 2, and if the sun is a star. Well, we still have 1 + 1 = 2, regardless of the status of the sun, right? So this will be provable. They'll be able to prove this, hopefully by Monday. So you can find out what an expression means by assigning a value to the variables and then simplifying. But what we're going to try to do in this class is to avoid doing that. It's like when you have a program and you say, oh, let me run my program on a particular input. Let me test it. Versus saying, I have a program and I can tell you a property about my program without ever running it. Right? Here is a fact that is true, regardless of what test cases you provide. So this sounds much better, right? That's like saying I have a bridge, and if you want to know if the bridge is going to collapse or not, let a baby walk over, let a mom walk over, let an adult walk over, let 3 adults walk over, let an elephant, and see every time. That's a very dangerous way to make a bridge. I don't recommend making bridges and testing them that way. You would not be licensed by the Professional Engineers of Ontario. Instead, you can do stress tests and be like, you know what? Here's a guarantee that the bridge, if you have 12 tons over it, that's much preferable. And so that's what we're going to do. We're going to say, hey, we're going to prove a theorem by moving the symbols around, by playing the game according to the specified rules. And when you play this game using these rules, the result is always going to be true. If you follow the rules, the result is always going to be a true theorem. Okay? And if you want, you can always assign values to the variables, and it will be true. Right? So this is a much more efficient way, and then you'll have CalCheck to check your work, and it's a nice process. And for programming, if you play the game with symbols instead of reasoning it informally, then the result can be cases, right? It's a double win. All right. Why did I put here? So some of you might still not be comfortable about precedence, and please just add parentheses where you feel is unclear to you. Okay. And I mentioned as a moment ago, the proof tables are just for confirming the Boolean laws, just to get that intuition. We're not going to do any Boolean tables in this class at all. Okay, so that's why chapter 2 is really quick. We're not actually going to do Boolean tables. To prove x plus y equals y plus x, are you going to list out all x values and all y values to make that check? No. So likewise, we're not going to waste time doing these things, but it's useful for the intuition. Okay, ducks. So as I mentioned a moment ago, so don't worry if you're not comfortable with the proof, but we said, t even if s, and we said you can prove that's equivalent to t. So hopefully you will be able to prove this in time, and you'll know what the steps mean. And you can formalize your intuition. So here's t and s implies t. Okay. If you look at the conjunction, so we assign values to t and s. S implies t has these values over here, and then the value of the whole conjunction is equal to this. Okay, but wait a minute. This is just the first row, right? So the whole expression t and s implies t is the same thing as just t. Okay, because the value is the same as the value of t. Okay, but this is not this doesn't scale. If your formula gets longer, right? If you have n variables in your formula, you will have a table of 2 to the power of n. Don't worry about the math. Well, right. For each variable, you can pick true or false, and there's n variables, so you have 2 to the power of n many choices. So you'll have a massive table. So if you have 10 variables, your table will have more than 1,000 columns, and that's a lot. Okay. If you have 4 variables, your table will be 16 lines long, and you've already proven things that involve 4 variables. So calculation is definitely better than enumeration. So just to show you that, and of course the proof is really cute, right? The proof is cute. It's readable. That table is not as readable. Like I had to point to a lot of things to explain it. So hopefully we're slowly convincing you of why calculation is preferable to enumeration. Okay. Here's how equivalence looks, and we just want to show you again. This is just to get the idea of why the axioms are the way they are. Like we say, this is that equivalence is associative. So if you look at the left-hand side, here's what it looks like as a truth table. And as I said a moment ago, we have 3 variables, p, q, and r. So how many rows does our table have? 2 to the power of 3, right? So it has 8 rows. That's a lot. All right, it's a cute little formula. This is, if some people think this is a proof, consider this to be a proof. Hand side, and you'll notice at every row they're the same. All right, they're the same at every row. And so we can conclude from this informal proof that they are the same, that they are equivalent. Okay. So we're using these Boolean truth tables to guide intuition and to tell us why the axioms are reasonable. All right. But the axioms are these God-given truths from which we play the game. Okay. It's like in Monopoly. Everyone starts with this much money, and then you walk around the board and try to get more money. All right. Or through the ages, when you have people and resources and you have to grow your economy, right? And you start off with the basic stuff and build from there. So the axioms are our building blocks, and then we derive theorems from them. So this is the next slide. Okay. So this is important, and this is important because it relates the idea of I play the game, and you told me that if I play the game, I will always end up with a theorem if I follow the rules. Okay. I never have to put values in there. I just play the game, follow the rules, and I'll always have a theorem. That sounds like magic. That sounds great. Okay. And the thing that lets us do that is this dandy result. Okay. We say an expression is satisfied in a particular assignment to values to variables if it's true in that assignment. Okay, so that's what satisfy means, and as we talked about before. And the interesting thing is, for the logic in this book, validity, right? So a Boolean expression is satisfied for every choice of values for variables. It's valid precisely when it's syntactically derivable from the rules and the axioms. Okay. So that's a nifty result. We're not going to prove it in this book. I can cite you to references that will do it. Not too difficult. I put a citation in the bridge lecture notes that refers to it if you want to see the proof. But yes, so there is a mathematical proof that says if you play this game, you'll always end up with a theorem. And the fact that this is a theorem, that is, it's valid, you can pick any values to variables, and the result is going to be true. So that's a really nice meta-mathematical result, right? Meta, like about or beyond or above. More examples about meta are in the supplemental notes. Okay, ducks. I would like to show you a thing right here. So there's a bunch of stuff on meta right here. If you're interested to learn more about how these phrases work in the logic, outside the logic. But this is the image I wanted to show you. Let's see if I can go full screen. Okay. So if you look at this image, you'll notice you have well-formed formulas, and so you have. Oh, I couldn't zoom in as much as I like. Sorry. So you. Oh, all right. I'm not allowed to type on this apparently. Okay. Nope. Can't type. Sorry. Okay. So the trunk of the tree is the axioms. These are your starting base, and from these you derive theorems. The top of the tree. Okay. So the white tree, the bottom of it is the axioms, and from those you apply the rules, and the rules will generate new true results. Okay. And that leads to the branches of the tree. Some logics will have truths that are not reachable. You can apply your rules as much as you want to the axioms to get new true things, and then you apply the rules to those new true things, and you'll get more parts of the tree, but you'll never get this shaded black part. There will be unreachable truths, so-called Gödel's incompleteness theorem, if you will. And then the opposite of a true fact is a false thing. So not true is equivalent to false, right? So this is the negation of theorems, right? And if you negate the axioms, and then there's going to be false things that we can never prove, right? That's kind of interesting. There's true things we can never prove, and there's false things we can never prove, and we're very lucky to be inside the tree. So I just wanted to show you that part. Okay, next. Again, this is all in chapter 2, all right, and covered perhaps a bit too extensively in the abridged lecture notes. All right. So what does equivalence mean when it's a chain, right? And again, just to show you the intuition, we assign values. There's 3 variables. So that means I have to pick true or false for each one of them. True or false, true or false, true or false. So 2 to the power of 3, that's 8 rows for my table. And if I notice in my table, I have some greens when there's one of them that's true. I have a green when one of them is true, and I have a green when all of them are true. And so we say one of the 3, one or all of them are true. Okay, let's look at a more general formula for this. Right? Just to explain this idea. So a continued equivalence of length 3 means one or all are true. You might have seen trichotomy before in calculus, which just says, given any 2 numbers, they're either one of them is to the left of one of them, or one of them is to the right of the other, or they're the same number. That's the first part of trichotomy. And then we say it cannot be all of these things at once. It's absurd to be the same number and greater than and less than. So it's got to be like this, or like this, right? So this just means one of the 3. Okay, so in particular, trichotomy says all 3. So we remove the second case. Okay, so here's some cool puzzles. Does anybody want to try to guess? How do we say none or both of P and Q is true? Does anybody want to take a guess? Somebody asked, does S imply true always equal true? Yes. Everything implies true. True is like positive infinity, and implies is like less than or equal to, and everything is less than or equal to positive infinity. More on that idea in the lecture notes. So does anybody want to try to guess the first one? None or both of P and Q is true? Somebody said P equivales Q. Yes, it is P equivales Q. What about the second one? The second one says exactly one of P and Q is true. So remember the Booleans, there's only true and false. And I want to say only one of them is true. So for only one of them to be true, that means the other one has to be false. So they're different. Okay, so they have to be different values, right? So that's just P differs from Q. Okay. So let me just show you the full solution. Okay. Yeah, so somebody guessed it. Good job. More people are guessing. I'm glad you are. So maybe let's do another one. It seems you're all getting, you're trying it out. So let's do another one. I have 4 variables, P, Q, R, S, and I want to know when is an even number of them going to be true? All right. When is an even number of them going to be true? How do I phrase this? All right. Does anyone have an answer? So I want an even number of P, Q, and R and S to be true. What do I do? All right. All right. So I have P, Q, R, and S, and I want to find out when is none of them going to be true, 2 of them going to be true, or 4 of them going to be true. Okay. Well, if there's any true, let's consider the equivalence operation, because that's what we're talking about. Whenever you have a chain of equivalences, any true can just be canceled out. Remember, true is the identity of equivalence. So if you ever have a true, you can just cancel it out, right? So if we want 0 of them to be true, okay, we can just phrase it as an equivalence. P equivales Q equivales R equivales S, right? And if 0 of them are true, that means they're all false, and false equals false equals false equals false is true. Everything is equal to itself. If I want 2 of them to be true, that means the other 2 are false. Remember, every true is popped away, you throw it away. And so I have 2 falses left, and false equals false is true. Okay, great. And if I want all 4 of them to be true, well, I'll have true equals true equals true equals true. So you can just use an equivalence. And for the last one, an inequivalence. Get to the solution. Yeah, I typed it up. Good job. Good job, Rubian and Iman. Okay, so here's the general form. So let me just point out a cool thing. So we talked about parity on the midterm, right? If you have a knight in chess, the knight always changes color, and the bishop always stays on the same color from the midterm. So that was even or odd parity. And I thought this was a cute way to phrase it, since you guys are comfortable with parity now. If you have a and and you want some of them to be true, then in the expression P1 equivales blah, 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 all the way to Pn, that one's going to be true precisely when the number of true items has the same parity as n. Okay. So if n is odd and you have odd many true things, then it's going to be true. If n is even and you have even many things, even many true things, then it's going to be true in those cases. So that's summarized up here, for example. Right? If you have an even number of propositions, so p to 2 times k, then you need an even number of truths, and that's how you'll make it true. And then likewise, if you have an even number of falses, you can make this one true. So notice this one doesn't care about parity, an even number of falses, because every time you have a false pair, false equals false, they cancel out. And so if there's an even number of them, you have enough pairs to cancel out, and then the result has to be true. The details will be in the supplemental in case you're interested. But just wanted to show you some cool stuff, that's all. So let's look at a few proofs. So we talked about this last time, and some people had a bit of trouble on the midterm. So I just want to point out this neat thing right here. Equality is equal to equivalence, and equality is equivalent to equivalence. All right, so that sounds like a tongue-in-cheek way to say things, but another way to say it is equals is equal to equals. They're all just equals. All right? Or equivalence is equivalent to equivalence. Right? So on the Booleans, equality and equivalence are the same concept. Equivalence is defined only for the Booleans. Equality is defined everywhere. And on the Booleans, they happen to be the same thing. Right? When you give it 2 arguments. Okay. And we said rather than plugging in values and checking, so rather than plug and chug, we have axioms that we talked about a moment ago using the truth tables. All right. So everything is equal to itself. That I think Bertrand Russell says that which is. If A is B, then B is A. All right. Transitivity lets us connect parts in a chain. So if I have X as the first step in my proof, and I derive an intermediary Y, and I end up all the way at Z, then I have X equals Z. Okay. And Leibniz says anywhere in place X is equal to it. Okay. So these are silent features of our presentation. Okay. They happen under the hood in our presentation. The calculational format lets us do these under the hood, which is a really nice feature. Okay. And as I said a moment ago, we have all of these. The last one, equanimity, also called equipollence, depending on who you ask. This is only in the newer edition of the book. Okay. And it just says, if I show something is equal to a theorem, then that thing is also a theorem. That's all. Okay. And you'll see it in CalCheck using the syntax this is. All right. You don't have to use that syntax, but it makes proofs shorter. So we'll get to it in time. Okay, dokes. All right. So this is what I mentioned a moment ago. All theorems in E are valid, and all valid expressions are theorems in E. You play the game, and you end up with a true result. Okay. So as long as you follow, you always end up with a true result. Right? So we're not going to use plug and chug. We're not going to do truth tables. We just wanted to show you this. We're never going to do it again. Right? It's important to understand that if you plug and chug, you'll get true. But using the moving symbols around, you also get true things. Okay, so if you play the game without thinking, you get true stuff. If you decide to think, that stuff is true. Okay, just another way to look at it. Okay, and it's really helpful to do things this way. And you'll see some examples of it. If you have a left-hand side and a right-hand side, and they look really different, instead of thinking about what they mean, you can say, oh, this is one drawing and that's another drawing. How do I make these drawings look similar? What rules let me change this art shape into that art shape? And you try to make the arts look closer and closer. And then when they're the same, you prove the theorem. So it's a different kind of game. It's very, very helpful. And hopefully we'll get to use it a lot in to prove that theorems are correct and to find ladies instead of tigers and to help Alice in Puzzle Land get the stolen goods and maybe we'll do some Castlevania problems and I think we're out of chess problems. I don't know that much about chess. I like Go, but anyhow, we'll see. Okay. So we looked at these theorems. So I'm just going to go over the next few slides a bit quickly because we've looked at them last week before the midterm. 3.4 says true is in fact a theorem. So that's pretty neat. Okay. So if you show something is equal to true, then that thing is a theorem. And that's because of equipollence or equanimity. Right. The previous one that says, hey, if you show something is equal to a theorem, then that thing is a theorem. All right. And 3.4 leads to something called a meta theorem. Again, the phrase meta is covered in the book. And meta just means theorems. And it essentially 3.4. Everything is equal to true. And so any two theorems are equivalent. Okay, so it's so all of these rules we mentioned earlier have a form via axioms or theorems as well. And the relationship between the two is also summarized in the supplemental notes in case you're interested. Okay, dokes. So we talked about this last time. I'm not going to spend too much time on it. The one thing I would like to point out is that in this class, we're going to say commutativity instead of distributivity for 3.9. Okay, as mentioned at the very beginning, using the name distributivity can be very people ask, how do I practice? How do I get better? So here's some rules for your game up here. These axioms are the rules. Now that you have these axioms and you know the rules, try to prove all of these theorems. Like, you know, stop the video, get a paper and pencil and just try to prove these. If you have access to a CalCheck notebook, open like a previous assignment or a previous homework from last week and try to prove these. Okay, that way you'll get more practice and you'll get faster and you'll know the theorems easier. You'll internalize them. So anytime you see a theorem, stop what you're doing, put the book down and be like, let me try to prove that theorem. Okay, if you struggle for maybe 30 minutes, you know, look at the answer, see how to prove it, and then the next day, try to prove the theorem again. All right, you saw the answer yesterday. Can you prove it again now by yourself? And just, you know, with sufficient practice, you'll remember the names, remember the precedents. You'll have a feeling of where to start and how to move forward. Okay, and the book has a lot of principles and heuristics. So I'll get to them in a moment. That helps guide you write your proofs. Okay. Did somebody say we're ever going to use theorem 3.4? No. Theorem 3.4 is, no, we're never going to use theorem 3.4. Almost never. You can use it for fun if you like. Where did it go? I'm sorry. Right here. Yeah. So yeah, you're almost never going to say, hey, true is a theorem. No. You're just, it's perhaps the least interesting theorem. It's useful because we show, you know, to prove a theorem P, we show P is equal to true, right? And because we showed P is equal to true by equanimity, we know that P must be true. And theorem 3.4 background explicitly. So 3.4 is useful because it's in the background, but we will never use it explicitly. Almost never. I think maybe we'll, you know, a few exercises, but almost never you'll use 3.4 explicitly. It's good to know that true is a theorem. Anyhow, here's some stuff from the midterm. Just as a reminder, inequivalence is also a symmetric, associative, mutually associates. The last one is probably new to some of you. As we talked last week, it's similar to how subtraction and addition work. Okay. You might see it in your assignment coming up soon. So we'll see about that. Here's a proof for symmetry of inequivalence. I really want to do a proof in front of you, but we're short on time. Sorry about that. So I'm just showing you the proof. Notice the first thing we do is we unfold. Okay, we don't know what this operation is, so we get rid of it by using its definition. Now we know what equivalence is and we know its operators. So we use that, then we fold up and to get back this new operator. So this is a common theme in this class. Whenever you have a new thing, you use the definition to get to familiar stuff, work with the familiar stuff, then go back to the new thing. Okay, and this is from the book. This is called the unfold fold strategy. Okay, so the book has a lot of and look at statistics. Please begin reading chapter 3 if you haven't. If you haven't, then you may not have done well on the midterm, and we are moving past chapter 3. So as I mentioned, got rid of it. Last step was the fold. We reintroduced it. Okay, so the book goes into detail about these kind of ideas if you're interested. Okay, looks. So we finally made it to this junction. Unfortunately, my clock says that we don't have a lot of time. We have 1 minute apparently. So maybe we'll just stop here and we'll continue with this junction tomorrow. And hopefully we'll make it up to implication. I'm gonna leave the channel open for you, so in case you can mimic the hallway scenario where you talk to people after lecture, and so I'm just gonna leave the channel. So please feel free to stay after I've left. Chat among yourselves and socialize and mingle and all that fun stuff. Bye. Actually, I'm still here.